right, can you all hear me? Awesome, great. So yeah, I know it says that I'm from Caltech, but I recently graduated and just started a postdoc at the University of Washington in Seattle in their astrobiology program there. And I'd like to start this final talk of the workshop with a question to you all, which is, what's the farthest that you have ever traveled for the holidays? Well, try competing with over 5 billion kilometers and nearly 13 years in deep space, because that's what the New Horizons spacecraft has to do to be with Kuiper Belt object MU69 this coming New Year's Day. And so we in the planetary community are all looking forward to this encounter with MU69. It's sure to be a very fascinating world full of scientific discoveries, but we don't know very much about it yet. And I would hate to try to speculate about it while I'm being recorded for all time. So mainly because we were so surprised by the last place that New Horizons went, which was Pluto. And that's going to be the subject for the bulk of this talk. So when New Horizons launched in 2006, Pluto was just a fuzzball of pixels to us. But thanks to New Horizons, today we know that Pluto is actually a winter wonderland, where alpine peaks are capped with methane snow, and there's a giant glacier of nitrogen ice that slowly convects, releasing residual internal heat, and where water ice is as hard as granite, unless, of course, it's being erupted from a possible cryovolcano. So these are some of my favorite sites that New Horizons has discovered on Pluto. But of course, you don't get to Pluto in under 10 years without picking up a really, really fast pace, about 14 kilometers per second. And so unfortunately, it was always New Horizons' destiny to fly right up to Pluto and then to sail right on past, never to be corralled into orbit. And as New Horizons flew past Pluto, it swung itself around to get one last look at everybody's favorite former planet. And what it saw was this: the bright, beautiful, brilliant blue organic haze in Pluto's atmosphere. And this is the part of Pluto that I want to focus on for most of this talk, the atmosphere of Pluto and the exciting and unique chemistry that we are learning from it. So just a few atmospheric basics to get everybody on the same page. Pluto has a surface pressure of about 10 microbars. That's 1/1,000,000th of the pressure at the surface of the Earth. It has a surface temperature of a frigid 40 Kelvin, although now after hearing all the talks from yesterday, I think 40 Kelvin sounds pretty warm. And the dominant constituents of Pluto's atmosphere is nitrogen gas with a little bit of methane. These are in vapor pressure equilibrium with the ices on its surface, so kind of a unique scenario there. And if you remember from Sarah Hurst's talk yesterday, these are the same two dominant constituents on Saturn's moon Titan, so we can expect that we can take some of our knowledge that we learned at Titan and bring it to our understanding of Pluto. Now, most of what we know about the composition of Pluto's atmosphere come from solar occultation. So that means that in this kind of view, as New Horizons is staring back at Pluto backlit by the sun, it watched as the disk of the sun passed behind one of Pluto's limbs and then sometime later emerged from the other side of Pluto. And during these events, it was able to detect the spectroscopic signatures of gases in Pluto's atmosphere absorbing out some of that ultraviolet sunlight. And immediately, there was a conundrum. So here I'm plotting for you the number density of certain gaseous species in Pluto's atmosphere against the altitude in Pluto's atmosphere. So we've got C2H2 acetylene, C2H4 ethylene, and C2H6 ethane. And these are the major photochemical products of methane photolysis. And you can see that there's some deviation between the data, which is represented by the circles, and photochemical models, which are the lines. And so the models and the data correspond pretty well in the upper regions of Pluto's atmosphere, above about 400 kilometers or so. But then all of a sudden, the actual profiles of these molecules deviates and decreases. So there's an underabundance from what we would expect from photochemistry. And there's this characteristic kink to the curve, and then a minimum in all of these profiles at around 200 kilometers. So one of our first jobs in trying to tell the story of the chemistry in Pluto's atmosphere was to try to explain this conundrum. And it turns out that you can't understand the gaseous profiles in Pluto's atmosphere without understanding what's going on with the solid particles in Pluto's atmosphere, the haze particles that I showed you in that previous image. And so let me now plot for you the extinction coefficient of the haze that New Horizons saw versus, again, altitude in Pluto's atmosphere, this time only going up to about 400 kilometers. It's kind of a busy plot, so let me walk you through what the different symbols mean. So the observations, again, are in the circles with their error bars, and they're separated by color for the ingress and the egress measurements. And what you should be able to tell from this is that the ingress and egress are fairly similar. There might be some slight inhomogeneity, but this jives with our understanding from the images of Pluto that really it has a global, fairly uniform haze layer. The dashed lines and the dashed dot lines correspond to haze production models that we have run, and for those of you in the business, the model was the Karma model. This was primarily run by my colleague Peter Gao, and I contributed to this work while we were both grad students at Caltech. So for the model, we consider both two cases, one with spherical particles for the hazes and one for fractal aggregate particles. And we also consider two different monomer sizes, 5 and 10 nanometers. And what you should take away from this plot is that in a case where Pluto's haze particles are spherical, no matter what size you choose for the monomers, you can't reproduce the extinction coefficient that New Horizons measured. So one of the main conclusions of this work was that the aerosols in Pluto's atmosphere are fractal aggregate hazes, very similar to what we know about Titan's aerosols. And basically, you can think of these as big, fluffy, three-dimensional snowflakes. Okay? So to get a better physical intuition for what is going on in Pluto's atmosphere, I'm going to sort of gray out gray out all of these complicated dots and curves. And instead of plotting the extinction coefficient on the x-axis, now I'm going to plot the haze surface area per volume on the x-axis. So this monotonically increases with depth into Pluto's atmosphere. And the way we understand this is basically these haze particles are forming from monomers that are generated by photochemistry high up in the atmosphere. And then as the haze descends into Pluto's atmosphere, it encounters regions of higher and higher gas pressure and is able to congeal and agglomerate more and more gas particles into it and thus grow in size. So the haze particles grow in size as they descend into Pluto's atmosphere. Now, some very important work done by Adrian Luspé-Kuti and colleagues, I apologize if I'm mispronouncing that name, showed that not only do these haze particles grow in size as they descend into Pluto's atmosphere, but they also age and harden. So what does that mean to age and harden? It means that they get less sticky. So here I've plotted the derived sticking efficiency for a haze particle with ethylene, for example, derived by Luspé-Kuti's work. And you can see that at around 400 kilometers, it goes from some non-zero value basically to vanishingly small at the surface. So to get microphysical intuition for what's going on here, I have a little cartoon, an encounter between a haze particle and a gaseous molecule. So when a gas molecule encounters a fractal aggregate haze, there's two options. One is that it sticks and the other that it doesn't. And the sticking efficiency gives you the probability that upon encounter, a gas molecule will actually stick. If it does stick, it's because of weak intermolecular interactions like van der Waals forces binding it to the surface of this fractal aggregate haze. When this happens, the gas molecule maintains its chemical identity. But if there is excess energy after this sticking process happens, such that you can induce a bimolecular reaction on the surface of this aerosol grain, then you can actually get complete sorption of this molecule into that haze particle. And I want to make the distinction between this process and condensation. It's very important. The gas molecules in this case aren't in a different phase on the surface of a grain and can readily evaporate or sublimate back into the atmosphere should the pressure and temperature conditions change. They're actually completely gone. They have fused chemically with the haze particle and formed a particle of a completely new chemical identity. So it's hard for them to get back into the atmosphere. And lab work has shown that organic aerosols made of hydrocarbons and nitriles formed in this way and hardened by ultraviolet radiation indeed do get less sticky due to chain elongation and polymer crossing and so forth. So let me show this slide again, the sticking coefficient and the haze surface area per volume with respect to altitude in Pluto's atmosphere. And you can see that these are really two competing effects for what's going on. And I think if I brought Goldilocks to Pluto and I asked her to assess what is going on in Pluto's atmosphere, I think Goldilocks would say something like this. Up in the higher regions of Pluto's atmosphere, above 300, 400 kilometers or so, there's just not a lot of haze surface area to be playing a very important role in controlling the gas abundances in Pluto's atmosphere. And deep in the atmosphere, below about 100 kilometers or so, although there are plenty of haze surface areas for molecules to bump into, it's just not very sticky, so those molecules won't actually get into the haze particles. But there's a region in Pluto's atmosphere around 200 kilometers where the conditions are just right for the haze particles to play an important role in sucking out the gas molecules and not letting them go back into the atmosphere. So once again, this was the conundrum that we were trying to solve. Why do these profiles of the gaseous hydrocarbons exhibit this strange feature? And again, you can't explain this from straight photochemistry alone, but if we tweak our photochemical models to allow for the gaseous removal onto these aerosol grains, and we tweak the sticking coefficients to try to match these curves, we can actually reproduce what is going on in Pluto's atmosphere. So the main takeaway from this work is that heterogeneous chemistry is very important in Pluto's atmosphere. You can't understand the gaseous abundances without taking into account their removal onto grain surfaces, which are also being generated by photochemistry in Pluto's atmosphere. So, that's very difficult to see on this big screen, but hopefully you can check it out on the smaller screens. New Horizons flew by Pluto over 3 years ago, but there is no lack of data left to mine. I'm showing you here some work in progress by a colleague of mine at Caltech, Sitong Fan, who is trying to use a Markov chain Monte Carlo method to back out and retrieve these very specific haze properties, such as its fractal dimension, the size of the monomers that are going into each haze particle, the number of monomers in each haze particle, and the number density of haze particles in Pluto's atmosphere with respect to altitude. And so I'm showing here an example staircase plot of his posterior probability distributions that he's derived for these haze particles at an example of 27.5 kilometers. But in principle, what he can do is understand how these parameters are changing at different altitudes in Pluto's atmosphere, given the full suite of data that we now have from New Horizons, and really use this to address the story that we've been telling about these haze particles growing and then becoming less and less fractal-like and filling in and hardening as they descend into Pluto's atmosphere. So if you're interested in this, please stay tuned for this work to come out soon. It turns out that the haze particles in Pluto's atmosphere are not just important for controlling the gaseous abundances of molecules in the atmosphere, but may also be extremely important in controlling the thermal profile of Pluto's atmosphere. So there was another huge conundrum in the atmospheric community when we got our data back from New Horizons. Before New Horizons got to Pluto, we all basically expected that Pluto's thermal structure would look something like the orange curve on this graph, with a peak temperature around 130 Kelvin or so, and then going to somewhat isothermal, about 100 Kelvin. Instead, what New Horizons found is that the temperature profile on Pluto is in some places 50 to 60 Kelvin cooler than we expected. So it has a maximum temperature of about 105 Kelvin, very, very near the surface, and then goes isothermal somewhere between 60 and 70 Kelvin. And this can be explained according to work by Xi Zhang and colleagues. Xi Zhang is a professor at UC Santa Cruz. And basically in his model, he explains this by cooling by the haze. So in this model, gaseous particles are donating their thermal energy to haze by collisions. And then the haze is very effective at radiating this energy back to space in the long wavelength infrared. And this theory can be tested by the James Webb Space Telescope. And so what I'm showing here is the thermal spectra of numerous things. So we've got Pluto's surface, its black body emission shown in the gray line, Pluto and Charon together in the dashed gray line. That's what the thermal spectrum should look like if the haze is not contributing to the long wave radiation coming out of Pluto. But if the haze is, then what we should see is something like the colored spectra. Now, again, we don't know exactly what the composition of these haze particles is. We don't know what the exact optical properties of these haze particles are either. So there's some room to tweak these models. But for all of the models that are physically consistent with what we think about haze production. They're fairly distinct from the simple surface blackbody radiation and should be easily distinguishable from that blackbody radiation by the James Webb Space Telescope's mid-infrared instrument, for which I've shown the 10 sigma detection limits for for the 10,000 second integration time here. So this is just reason number 47,582 that we planetary scientists and astronomers are looking forward to the James Webb Space Telescope's launch. So I want to conclude this Pluto section by saying that Pluto is nature's laboratory for organosynthesis at what I would call, as a planetary scientist studying planetary atmospheres, low pressures and temperatures, but I realize now that to the astrochemical community, Pluto is actually pretty high temperature and pressure. But nonetheless, it is a unique pressure and temperature space that we are just exploring for the first time and learning a great deal about. And for those of you with laboratories at home or who run ab initio simulations, I think the broader chemical and chemical engineering community can contribute to our story about Pluto by trying to validate the things that we're claiming is happening on Pluto. Please, if you can reach these pressures and temperatures in your labs, help us measure those sticking coefficients, help us measure the saturation vapor pressures of these gases, and so forth and so on, the rate coefficients, try to get at those with your simulations or your lab work, and bolster our confidence that the story that we're telling for Pluto is actually the right one. So while there's plenty of exciting atmospheric chemistry happening on Pluto, I mentioned cryovolcanism. Are we seeing some organics that have been processed in hidden aqueous environments from the subsurface? And I'm just going to leave that as a question for now, because maybe there might be a paper that may come out in a high-impact journal, maybe soon, but I don't want to say any more than that, because otherwise somebody may come for my head. So let's just leave it at that. If that paper does come out and you see it, act surprised, and don't tell anybody that you heard it from me. But there's the possibility that there's some subsurface alteration of organics on Pluto as well. But while that's still speculation for right now, we do know that this subsurface alteration of organics and processing of organics does happen in the outer solar system. So I want to turn our attention to the ocean worlds for the rest of this talk. And we were given a great introduction to the ocean worlds by Professor Stockton in the last talk. That's great. I think that there's not enough that can be said about why these worlds are exciting. So in particular, Europa and Enceladus, they house global subsurface oceans beneath their icy crusts. And for this reason, Europa could have up to twice the volume of liquid water inside of this tiny moon of Jupiter as the entire Earth itself. And so for this reason, we think that they are very prime prospects for astrobiological research. And so let me summarize once again why these places might be not such a bad place to live. As I take a sip of my liquid water is very important for all life as we know it. And the reason is this: what does life do? What does life need to live? Well, we all need a source of free energy. And we get that free energy by transferring electrons from the reductants, or the food that we eat, to the oxidants, or in our case, the air that we breathe. And we do this through aqueous chemistry, right? So it turns out that Europa's got plenty of liquid water thanks to the tidal forces that keep it warm and slushy. It also has plenty of oxidants being generated at its surface from radiolysis. So this is by high energy particles that are trapped in Jupiter's magnetosphere, impacting the surface. Some of these particles, especially the heavier ions, are sourced from Europa's sister satellite, Io. And so when these particles impact the icy surface, they sputter away hydrogen and leave more oxidized compounds that can possibly then get subducted back into, or subducted down into the ocean. In addition, as Amanda mentioned, there's a real good chance for hydrothermal activity at the water-rock interface of Europa, and that would give the reductants through a process, as she mentioned, serpentinization. So for all intents and purposes, Europa is probably a pretty habitable environment, but the question of habitability and inhabitation are subtly different but very important. So as Amanda said, there are theories for abiogenesis, or for the emergence of life, that have been applied to early Earth that can also be ported to the icy moons. And in particular, we're speaking about the alkaline hydrothermal vent hypothesis, which is basically, in very technical terms, denitrifying methanotrophic acetogenesis. And in these environments, basically you have a pH gradient and an electrochemical gradient, redox gradient, that can drive the synthesis of biological activity. Okay. And so, yes. Okay, we're going to go to Europa in the future with missions such as the Europa Clipper mission. And Europa Clipper will basically send a bunch of spectrometers and sounders and dust analyzers to try to understand the surface and subsurface processes of Europa to assess its habitability. But it should be noted that most of what the Clipper will do for Europa has already been done by Cassini for Saturn's moon Enceladus. So for this very final portion of the talk, I want to pull us away from the Jovian system and send us to Saturn. And this is very difficult to see. Maybe you can see on your monitors. Let's play a game. In 5 seconds, can you spot where Enceladus is on this image? It's a very small moon of Saturn, so I don't blame you if you can't see it. But if you think you can, find this moon that is the size of England. Point to it right now. Ah, Amanda knows, so there you go. You got it right. Enceladus is right there. It's embedded in this diffuse ring called the E ring, which is actually sourced from particles that are ejected by the jets at Enceladus' south pole. And just for fun, Earth is also in this image right there. That's everybody you've ever known. Okay, so the Cassini spacecraft flew through these E-ring particles and sampled them with the cosmic dust analyzer, found sodium-bearing salts in these particles. That's indicative of a water-rock interface, which again is very exciting. Gives the possibility of hydrothermal activity. Later analysis of the cosmic dust analyzer showed that these E-ring particles also contain silica-rich grains. And so our geochemical friends tell us that this is indicative of ongoing hydrothermal activity right now. And the case for ongoing hydrothermal activity was bolstered just last year when it was reported that in Cassini's final flyby through Enceladus' plumes themselves, it opened up its ion-neutral mass spectrometer to this open source mode, which greatly reduced the background hydrogen that was being produced in these measurements by interaction between water and the metal components of the instrument itself. And so the background measurements of water are these blue lines, greatly reduced, and we're able to get a handle on how much mass 2 stuff there is, in other words, how much hydrogen gas is coming out of Enceladus' plumes. And the measurement was a flux of 1 to 5 billion moles per year. For those of us who don't like to think in moles and rather like to think in pizzas, some quick calculations show that this was equivalent to about 300 pizzas per year. So plenty of energy on Enceladus. We've got hydrogen. CO2 has also been measured. Are these things reacting to form organics? Indeed they are. So this is some early INMS spectra, mass spectra showing plenty of organics, small molecules, water, methane, ammonia, but then also organic compounds all the way up to things that are related to benzene. And then as Amanda showed, earlier this year we also found evidence for high mass organic compounds that are likely fragments from something even larger, something greater than atomic mass unit 200. So plenty of organics, probably being created by some kind of Fischer-Tropsch synthesis, that is H2 and CO2 reacting, spurred on by catalytic minerals at the seafloor. But the question on everybody's mind is, are these things fragments of perhaps life, something like DNA, something like proteins, something like lipids? And I think that it's really time to take seriously the possibility of going back to Enceladus with higher resolution mass spectrometers and searching for biosignatures. We had a good discussion of different ways of looking for biosignatures in the previous talks. I prefer, as Amanda does, to look for agnostic signs of life. That means not to look for specific products of life, because in that is baked in a lot of assumptions of the biochemistry of exobiological systems, but rather to look for the general processes that we expect life to do. So one of the great hallmarks of life, indeed, that is a necessity to what life really is disequilibrium. Okay, and so what we've found here on Earth is that abiological systems that produce organics have this very normal shaped curve in terms of their abundance versus their molecular weight. This is driven by thermodynamics. Whereas living systems that produce organics produce these sharply peaked abundances around things that biomolecules that are very specific to what we need. So, for instance, we create a lot of ATP, we create a lot of the 20 amino acids that we use, and not the full spectrum of organic molecules that are possible. So when we go to a place like Enceladus, what we're looking for is not necessarily the same nucleic acids or the same amino acids that we use, but a distribution of organics that is equally out of equilibrium as the biochemistry in our own bodies. So to conclude, I want to say that these ocean worlds are nature's laboratories for organosynthesis at water-rock reactions, and we're really just scratching the surface of what is down there and what is happening. And I think that as a community, we should really come together as chemists, astronomers, planetary scientists, astrobiologists, theoretical physicists, and try to understand the big questions that Sarah posed at the top of her talk yesterday. You know, why are we here? How did we get here? Are we alone? What is our place in the universe? And I think that we can use the techniques of chemistry that we've been honing for the past several hundred years to really guide us to those answers today. Thank you.
Time for a quick question.
You kind of painted a picture that there wasn't movement of the particles in the atmosphere of Pluto. Is that correct? I mean, you showed it being very stratified. That seems to be counterintuitive to me. That the particles fall and then stay down. They don't ever go back up in the atmosphere?
Yeah, I would say that there's a lot of ongoing work on the dynamics of Pluto's atmosphere, but it is generally assumed that these haze particles are slowly descending through Pluto's atmosphere and then settle out on the surface. So some of the coloration on Pluto's surface is thought to be basically these tholin-like particles that are painting Pluto's surface sort of this brownish, orangish, even reddish material. Yeah.
Another question? I think we should move on to the panel, so let's thank the speaker again.